Hello, you're welcome. All right, so now the topic before us is temperature, okay, and measurement. All right, so now we're gonna start by defining the temperature, right? Now, temperature is actually defined as a physical quantity, right? A temperature is simple a physical quantity, okay, which is actually used to measure, right, the heat, which actually measures the heat content of a body, or which indicates, okay, the heat content of a body. Now, of course, if a body has, if the heat of a body is high, okay, we could actually measure that by the temperature of that particular body. So, high temperature actually is equivalent to a very high heat, right? Now, okay, there's another definition, which of course is very common, right? And that definition is temperature is actually been defined as the degree of coldness and hotness of a body. All right. Now, this particular definition is not ideal because if you are talking about, if you want to look at temperatures in terms of the degree of coldness and hotness of a body, okay, you discover that you are actually looking at temperature being measured by feeling, okay, to feel feeling of coldness and hotness, and the feeling of coldness or hotness does not give you an accurate result, an accurate um, measurement of temperature, because feelings is subject to body temperature. Any if you want to feel the temperature, okay, the result you have or the perception you get depends on your own body temperature. Okay, this is what happens probably when you find yourself in an air conditioned room for a very long time. When you come out outside the air conditioner room, you discover that every place feel very hot, okay. Now, because your body was actually conditioned by the coldness of that environment, so coming outside now by uh, feelings, okay, which of course is being affected by the condition that your body, okay, we are subjected to previously, give you this perception that the outside is hot, but it's not. All right, so feeling is not an ideal way of actually measuring temperature, right? So the only way to measure temperature is to actually measure temperature using physical quantities, okay, physical quantity which actually changes, all right, that doesn't have any form of emotional constraint, all right, that could actually measure temperature at accurate temperature at a particular time. So now actually go to subtopic, which of course is the actual measurement of temperature, right? Okay. All right, so measurement of temperature. How do we measure temperature? Of course, feeling is not an accurate way of measuring temperature. You can't just touch a body to actually dictate the temperature of that particular body. So there's an accurate method of actually measuring temperature. Now, the accurate method of measuring temperature is to use some substances, okay, which are known as thermometric substance. Thermometric substance. Right? Thermometric substance are substances that is actually used to construct a thermometer, okay, used for temperature measurement, because they will definitely give you an accurate value. Now, the reason being that for a thermometric substance, okay, these substances, what happens is that their physical properties, right? Their physical properties actually changes. physical properties, all right, changes, all right, with the change in temperature, with temperature. All right, so because of that, because they have physical properties which only changes with temperature, we can actually utilize those physical properties to actually construct a thermometer that is used for temperature measurement. So let's look at example of thermometric substance, right? Number one thermometric substance is mercury, all right? It's mercury. All right, mercury is actually used in construction of mercury in glass thermometer, and of course, what is the property of mercury that actually changes with temperature? Okay, for mercury, the property of mercury that changes with temperature is thermal expansion. Thermal expansion, right? So which it simply means that when mercury is actually being subjected to heat, right, it expands according to the amount of heat that is actually being subjected to it, right? So we actually utilize that to construct a thermometer so that if you don't want to measure a body, just use a mercury in glass thermometer, right? Bring the mercury in glass thermometer in contact with that body, and of course, the amount of heat content of that body will cause the mercury to rise, okay, to expand, to rise in the column, and you can actually you measure um, the temperature, right? So this is number one. This is number one thermometric substance, right? Alcohol is also a thermometric substance that actually involve thermal expansion, right? Now, there are some thermometric substances that actually involve change in resistance with temperature, right? Uh, we have platinum. Platinum is a thermometric substance, all right? But platinum works with change in its resistance. Change in resistance. Alright. So which simply means that for platinum, okay, a thermometer that is actually constructed with platinum, okay, the physical properties of platinum that changes with temperature is the resistance, alright. So when the temperature changes, the resistance of the thermometer of platinum changes. So we can use that to construct a thermometer, right, known as resistance thermometer, right. So platinum is used in constructing. Example of thermometer that's constructed with the platinum is resistance thermometer. All right. Okay, so let's proceed. Let's look at so we have pressure, right? Change in pressure of gas. So we are looking at gas being a substance, okay, that can also be used to construct a thermometer, right? Now, one thing about gas is that when the temperature of gas actually increases, right, pressure of the gas actually changes. Okay, pressure changes at a constant volume. So we can actually example of such thermometer is known as constant volume thermometer. So the gas, all right, is being confined in a container, then with temperature being increased, okay, and of course for gas I believe that such temperature that we can use constant volume thermometer to uh, constant volume gas thermometer to measure is actually very high temperature, right? So such a temperature has the ability of actually changing the pressure of the gas so that it can actually be the temperature can be measured. So now we also have another example. Another example is okay, a device known as a thermocouple. A thermocouple is just two wire, okay? Um, Thermocouple, right? So two conductors joined together, okay? And of course, what changes in a thermocouple is actually EMF, changing EMF, changing in EMF, electromotive force. So a thermocouple is actually made up of two wires, all right? Two wires that is actually joined together, two wire of that has different coefficient, all right, temperature coefficient of resistance joined together, all right. So what happens is this: anytime those two wires actually experience a kind of change in temperature, okay, that will be what EMF is actually being generated due to that change in temperature, and that can be used to construct a thermometer known as a thermocouple, right? So please take note of that. All right, so on and so forth. So we are going to proceed, okay, to the next subtopic. So here we are going to be talking about, now we know that, all right, for us to actually measure temperature accurately, we need a thermometer, and we also know that a thermometer is being constructed using a substance known as thermometric substance. Okay, now having gotten a thermometric substance, and of course, how do you actually use that thermometric substance to actually construct a thermometer? All right, if you have to do that, you must calibrate such thermometer. Calibration means you need to actually write a scale on the body of that thermometer so that it can measure the accurate temperature. So to do that, you need to create what is known as temperature scale, depending on, okay, the kind of scale you want to use in that thermometer. Okay, so we are going to be talking about temperature scale now. Now, there are different temperature scale we can use for thermometer, but we look at some standard temperature scale, okay, that we can use in calibrating a thermometer. Now, one of the scale we're going to talk about is a Celsius scale. All right. We also have another scale known as a Fahrenheit scale. Fahrenheit temperature scale. Then we also have what is also known as, of course, the actual temperature, which is the standard temperature measurement scale. Okay, that's Kelvin scale. All right, so now for these scales, we use it to calibrate the thermometer. Now, for you to actually calibrate a thermometer, all right, you must have two fixed points. Now, what I mean by fixed point is that you must have the lowest temperature that thermometer will measure, and of course, you must have the highest temperature. All right, so this gives us two fixed points, lower and upper fixed point. All right, so we'll talk about thermometer fixed points. All right, so the very first fixed point you're going to talk about is the lower fixed point. Lower fixed point. Okay. All right. Now, the lower the fixed point of a thermometer is the lowest temperature which you can measure. Now, by the standard scales we have, okay, remember, among all the scale, the one of the standard scale we're gonna be using, okay, for our fixed point is gonna be the Celsius scale. Now, lower fixed point is simply the we use by standard, okay, is the temperature of a melting ice. So that is the lowest temperature, right? So we use temperature of melting ice, all right, as our, okay, as a standard for measuring, or as a standard value for the lower the lower fixed point. Temperature of, and of course, you know that I is met at 0 degrees Celsius, right? So lower fixed point is simply 0 degrees Celsius. All right. Then, of course, the other fixed point, which of course is the upper fixed point, that is the maximum temperature, right? Upper fixed point. All right. So now this upper fixed point is for centigrade is actually of course the temperature of a boiling water, and of course at boiling water we're looking at steam, not just because if we want to actually measure the accurately, we're going to be looking at for upper fixed point. Okay, so it's going to be the temperature of a steam. All right, and of course we know that it is equal to 100 degrees Celsius. So we can actually do compare and comparison. Okay, I use Celsius to represent we can do comparison, please pardon my English. All right, so here we go. So for all this scales, I can actually indicate use horizontal line to represent both the upper and the lower fixed point. So I'm gonna start with that of Celsius. All right, please I'm always use Celsius, right, as my standard. So for lower fixed point of Celsius or centigrade, remember it's centigrade scale, right? We have 0 degrees Celsius, and of course upper, that's 100 degrees Celsius, right? So you write it up here. Lower, so in between now are temperature that can be measured in between. So you can calibrate between the lower fixed point and the upper fixed point. All right, so what of Fahrenheit? Is it the same with Fahrenheit? No. Okay, it's not the same with Fahrenheit. So I will still gonna draw the fixed point of Fahrenheit, right? For Fahrenheit, the lower fixed point is kind of higher. That's 32 degrees Fahrenheit. Then the upper fixed point of Fahrenheit is 212 degrees Fahrenheit. So I will talk about Kelvin later, right? So you can see that is how you actually calibrate lower and upper. So you can always interconvert from Fahrenheit to Celsius, from Celsius to Fahrenheit. It's just very easy, okay? Anytime you are being given a question for you to, for example, they ask you, what is the temperature in the Celsius, okay, that is equivalent to, let's say, 40 degrees Fahrenheit. So you're looking for a temperature that is actually that matches with 40 degrees Fahrenheit. So you can call it theta. So it's just very easy, okay? So all you just need to do is just to take the difference in the scale. How do I solve this, right? Okay, so to do this, I'm going to take the difference between the upper and lower fixed point of the Celsius scale. That is going to be, the difference is going to be, or the distance, that is 100 minus 0. From 0 to 100, okay? That's the distance. Then after the difference between that temperature I'm actually looking for from the lower fixed point, that's going to be theta minus 0. So this is for the Celsius. It's also equivalent, it's equal to what I do in the Fahrenheit, right? Between upper and lower, that's going to be 212, excuse me. That's going to be 212, then minus 32, right, all divided by 40, okay, minus 32. All right, so let's flow. So this is going to be equal to 100 theta minus 0 is theta. I'm equal to 212 minus 32. Okay. Write that very well. 212 minus 32, that gives me 180. So 40 minus 32, that gives me 8. All I just need to just for me to cross multiply. If I cross multiply, I'm gonna have 180 theta is equal to 800, right? So theta definitely is gonna be equal to 800 divided by 180. So that is how you convert. I'm gonna give you more examples. All right. Anytime you are being asked to any question that involves temperature conversion, just simple compare that temperature that you want to convert with the Celsius scale, all right, temperature scale. Okay, in any conversion, you just use that and you can get your answer. All right. Okay. Now, before we actually get to the questions, let's actually proceed, right, with the Kelvin scale. Now, if I'm actually talking about Kelvin scale, okay, of course, you know that the standard SI unit or the SI unit of temperature is in Kelvin, all right? So that is why we have what is known as the absolute temperature. So we call it absolute temperature. So absolute temperature is simply the temperature that is actually measured in Kelvin, okay? Absolute temperature is temperature that is measured in Kelvin. All right, so Kelvin actually is the SI unit of temperature, so we call it absolute temperature. Now the question is this, okay, if we have, how do we convert between Celsius to Kelvin? Okay, so that's what we're going to look at now. Let's say you are being given temperature in Celsius, how do we convert it to Kelvin? So converting, right, from Celsius to Kelvin. All right, so now it's very easy. Let's say you are being given let's say the temperature in Celsius is theta degrees Celsius, all right, and you want to convert this to Kelvin, right? So if I want to convert this, let me just use scale to represent temperature in Kelvin. All I just need to do is just add 273 to this temperature. So anytime you want to convert any temperature, okay, from Celsius to Kelvin, add 273 to it. For example, 27 degrees Celsius. All right, you are asked to convert this to Kelvin. Simple. So the temperature in Kelvin is gonna be add 273 to 27. So that gives me 300 Kelvin. So that is how we convert from Celsius to Kelvin. All right. So you now discover that Kelvin is much higher than Celsius. Much higher. That means invariably now, if I'm having zero, if temperature in Celsius, all right, is simply, let's say, 0 degrees Celsius. Because when we say zero, we say that there's no temperature. Now you should take note of this. The fact that temperature is 0 degrees Celsius doesn't mean that there is no heat. Because 0 degrees Celsius, if I should convert 0 degrees Celsius to Kelvin, okay, it won't be 0 Kelvin. Why? Because that's gonna be 0, right? Then plus 273. Right? So that means even 0 degrees Celsius, right, is equivalent to 273 Kelvin. So that still heats. The temperature is not 0 when it is 0 degrees Celsius. The only time temperature is 0 is when it is 0 Kelvin, okay? And that is what we call it absolute zero. Alright? absolute zero. So absolute zero is simply 0 Kelvin. And what happened at absolute zero? At absolute zero, whenever the temperature of a particular substance, or let's use gas, okay, for example, is actually at absolute zero, it simply means that such gas, all right, have no energy. Okay, at the point of absolute zero, there's no heat energy again. You can't get any no heat energy present. And of course, you know that, all right, temperature is not an energy, heat is an energy. All right, okay, what temperature does is to actually measures, it actually indicates there is heat on the body, right? But the actual energy is heat. So at absolute zero, we can say that there's no heat energy. Why? Because it is zero, it at that point 0 degree Kelvin. And of course, how do I know there's no energy at all? Right, if zero is low, so 0 Celsius is low. That means if I should convert 0 Kelvin, okay, let's say I have 0 Kelvin, I want to convert 0 Kelvin to Celsius, to temperature in Celsius. That would be 0, okay, plus theta, all right, degree Celsius plus 273. So if I should make the theta, all right, temperature in degrees Celsius, the subject, now that's going to be equal to, I'll take this to the other side, it becomes minus 273. So I see how low it is. So that means 0 degree Kelvin is as low as minus 273, negative 273 degree Celsius. All right. So that is why I call it what. So at this particular temperature, there is absolutely no heat energy present in that particular substance. So I hope that is well understood. All right. So I want to seize this opportunity to talk about different types of thermometer, but I will start with clinical thermometer. All right. So of course, this thermometer that is actually used in clinic, though there is a whole lot of modification have taken place, and of course it's not what it used to be before, but we still use the clinical thermometer that is a form of mercury in glass. Okay, mercury in a glass, right? That's one. Let me draw that. So this is just to have a glass tube, all right, with a tiny, inside the glass tube there's a tiny capillary, okay, like capillary tube, like what you have as in your pen, all right, the tiny tube in the pen. Then inside it will have mercury being inserted, right? There's a bulb, a place, the reservoir where you actually put mercury. Remember, clinical thermometer is actually mercury in glass thermometer, right? Right. So this place is where you actually insert mercury, okay, where you actually put in mercury. Then of course at this some point, okay, in this term there's going to be a kind of curvature. That curvature is what is known as constriction. I'll tell you why you have such curvature in that tube, right? So mercury actually rises from the bulb where it's being placed, okay, and of course the glass tube is being calibrated in degrees Celsius, right? Calibrated degrees Celsius. So when you actually place it on the body, of course, you know what happened now, thermal expansion, the mercury expands according to the amount of heat it is actually being subjected to. All right, so it actually expands and rises in the capillary so that you could actually reach the actual temperature. But now, what is the essence of this constriction? Remember, if you're actually measuring body temperature, okay, if I don't have this constriction, if I place this thermometer on the body that I want to measure the temperature, by the time I remove it, when the temperature is not there, remember, mercury only expands when there's a temperature is high. If the temperature is no longer, if the heat, okay, pardon me, is no longer there, it will still need to come back. And of course, you need to actually read the value before the mercury returns. right? So you discover that without this constriction actually helps, so that when this mercury actually rises, okay, actually rises to the point where you want to read the actual value. Okay, this constriction, please pardon my diagram, is actually down here before the calibration. So it's down. Let me do that very well so that not get you confused. Okay, before you even start the calibration, that is where you have the constriction. Okay, all right, so somewhere around the calibration. Okay, so all right, of course, pardon my diagram. So that simply means the constriction actually helps so that the person that's taking the measurement could actually read the value of the temperature, okay, then so that before even the mercury, and of course this constriction will prevent the mercury from returning back. So the only way mercury in that particular capillarity can return back is when you vigorously shake the thermometer, okay, for another reading. So I hope that's well understood. Okay, so that's mercury. So of course mercury in glass thermometer of course makes use of what? Mercury, which of course the clinical thermometer, it makes use of mercury as the thermometric substance. We call it, it can also, okay, it was also constructed, okay, previously with alcohol as a thermometric substance. Now these two things are regarded as thermometric liquid. We call them thermometric because they are in their liquid form, right? So we call them thermometric liquids. Okay, both mercury and alcohol are referred to as thermometric liquids because they are in their liquid form. And of course, their properties that actually changes with temperature is their thermal expansion. When there is heat, all right, due to that rise in temperature, they will actually expand. But the question is, there's always an advantage between this. And of course, we discovered that mercury is now used over alcohol. The question is why? What is the advantage that mercury have over alcohol, okay, as a thermometric substance? Now, one important, all right, properties that mercury have that makes it advantageous over alcohol is the fact that mercury is opaque. All right, of course, you know this is actually going to be, the mercury will be is going to be inserted into a transparent glass. So if the mercury is transparent, it will be very difficult for you to actually know the actual gauge or to take the reading of, okay, of that part of the position of the mercury, right? So that the opaque nature of mercury actually gives it an advantage, unlike alcohol that is transparent. So that makes alcohol very difficult. All right, so it makes it it gives an alcohol disadvantage, okay, as a thermometric liquid, right? So another advantage that mercury have over alcohol as a thermometric substance is that it does not wet. Well, God, does not wet, okay, does not wet glass. Okay, mercury can never wet a glass. So of course in physics we call such substance as cohesive substance that has cohesive force. Okay, that means the force of attraction between themselves is much stronger than the attraction with other substance like glass. Okay, so mercury doesn't wet glass, so it does any, if you are using it as a thermometric liquid, any position where the mercury, you see the mercury, okay, at any level where you see the mercury, that is the mercury there. It is not, it didn't wet the glass, that is where it is. All right, unlike alcohol which wet glass. Of course, when glass is being wetted, okay, if you've experienced when glass is being wetted even with water, because alcohol, okay, has that same transparent, and of course, uh, that kind of physical, property like that of water, okay, there's no difference. All right, so now, when water actually wets glass, you discover one thing, or probably if you have a bottle that is filled with water, sometimes you may not really know the level of the water because of the wetting of water, okay, the wetting of the glass by the water. Okay, so please take note of that. So that wetting of glass by water gives alcohol its advantage, and of course it gives mercury an advantage. Okay, if that is well understood. Okay, so basically that is one the advantage, okay, mercury have over alcohol as a thermometric substance. All right, and of course mercury is, if you also should go further, is has okay, a very low coefficient, excuse me, okay, has low coefficient of thermal expansion. Okay, is it low coefficient of thermal expansion? Okay, or low, let me just use low specific heat capacity, invariably low coefficient of thermal expansion. I will explain what that means. All right, coefficient of thermal expansion, of course, if we're actually describing it in terms of linear expansion, is defined as the increase in length per unit rise in temperature. All right, so per unit rise in temperature, the increase in length per unit rise in temperature. So if a substance has a low uh, specific heat capacity, okay, if I'm not mistaken, let me actually write the formula. Okay, if a substance have please pardon me, if a substance has, I call it alpha, that's why I call it alpha. Okay, if a substance has um, a high coefficient of linear expansion, right? Remember, linear expansion is actually given by the formula. All right, increase or change in length, all right, per unit length, then per unit rise in temperature. Okay, so from this formula now, we can simply say that, okay, if a substance has a low specific capacity, it simply means that the increase in length it will experience at a unit temperature, okay, is going to be low. So now for mercury, okay, please, mercury have high coefficient, which simply means that, okay, at just a unit rise in temperature of mercury, okay, gives a very considerable rise in the length of mercury. All right, it gives a considerable rise in the length of mercury. That simply means that mercury is actually more temperature sensitive than alcohol, right? Yes, because of its high coefficient of thermal expansion. So just a little change in temperature, rise in temperature, could actually cause mercury to rise significantly, okay, than what you will experience with alcohol. So that actually enhances sensitivity. Remember, one good property of a thermometer is that a thermometer should be sensitive to temperature, right? It should be sensitive even when the temperature rise, Okay, the thermometer should be sensitive. Even when the temperature rise is actually very small. Okay, a thermometer should actually detect that temperature rise. That is sensitivity. All right, a thermometer should also be accurate. Right, it should give an accurate value. A thermometer should give an accurate value. Okay, a thermometer should be reproducible. We'll talk more about all those the properties of thermometers. Okay, after we must have learned all different types of thermometer. They, of course, we'll talk about how to measure the sensitivity of a thermometer, right? So I'm only trying to describe what makes mercury more preferable, advantageous over alcohol, right? Okay, as a thermometric liquid. But alcohol have one advantage that mercury doesn't have. What is that one advantage that mercury doesn't have? Alcohol can measure low temperature than alcohol than mercury. Remember, mercury, okay, right? Alcohol measures very low temperature. All right, than mercury. Now, why is it so? Because the truth of a matter is the temperature, the amount, or okay, the level of temperature that any of these thermometric liquid can measure, all right, depends on their freezing point. Remember, both are liquids, all right? Okay, so alcohol actually freezes at a lower temperature, okay, than that of mercury. Mercury is actually almost, you look at mercury as a semi-liquid, all right? It's not actually a liquid, semi-liquid. It's a liquid that is very thick. Are you okay already? So if the temperature is low, all right, okay, if the temperature is low, before it actually gets to actually a particular low, the lowness of that temperature gets to a particular level, it has actually solidifies. Okay, so but for alcohol, it will, right, give you a value for a lower temperature than mercury. So please take note of that. Okay, so we are going to look at other types of thermometer, their construction, okay, their working principles, and we'll look at generally um, the properties, the quality, okay, of thermometer. So we'll do that in our next video. Right, see you in the next video. Thank you very much.